Okay, so good morning, ladies and gentlemen. Today I will provide an overview of what we are doing in Almaden using analog memory for deep learning. And this is just one of the many approaches that IBM is pursuing using novel technologies for deep learning. So, in my presentation, after a short introduction, I will basically describe why we think that analog memories are actually good for deep learning and what can be done with them. And after that, we will provide our new weight structure that can actually provide software equivalent training accuracies on deep neural networks. And after some circuit design considerations, basically how we need to design circuits to make things go fast, I will conclude my talk. So, it's 3 days we are talking about artificial intelligence, and I didn't remove this slide, but it's obvious to you. Basically, we can have a description of artificial intelligence like a collection of many different algorithms and schemes to solve real-world problems. And we can define two major families. The first one is the families of techniques which deal with machine learning. Here we find neural networks and deep learning, and these are not very brain-inspired, let's say. While then we evolve the families of algorithms which try to mimic what the brain actually does. We are more focused on this part of artificial intelligence, and we know that in the last years there has been a huge amount of development in AI due to the fact that we have an algorithm that works for training deep neural networks. We have a huge amount of labeled data, and that's important because without that we cannot train large networks for performing meaningful classification. And then we also have computational power. So we have in the last years hardware that performs a huge amount of computations. And we can see that, for example, in this figure, which just shows results on ImageNet. We all know that in the years there has been a steady increase in accuracy in the classification of this data set, even beyond the human level. However, this is possible. However, we also want to go on thanks to the fact that we have hardware that can perform computation very well. Nowadays, we can basically distinguish hardware in two categories for machine learning. First one is hardware that performs forward inference. So basically, we train a network in software, and we load pre-trained weights into hardware, and then the hardware can perform classifications very fast and efficiently. Second family is a family of hardware that can perform training, so hardware that can actually change the weights in a neural network. And this is today performed with CPUs and GPUs, but we are already starting to see custom digital accelerators, basically von Neumann structures based on a digital scheme that can perform forward inference or training more efficiently. Our goal is actually to go beyond these schemes and provide something that can train and perform forward inference even faster, and this is based on novel technologies, for example, analog memories. To understand why analog memories are actually good, we need to understand what is the most computationally expensive part in training and inference of neural networks. And this figure just shows a simple one-layer network. The output of this neuron is calculated as the sum of x, which is the output of the previous layer neurons, times w, the weight connecting neuron input with neuron output. This quantity is then passed through a nonlinearity, which enables complex computation, and we can perform many things with deep neural networks. In this simple formula, what is really expensive is the multiply and accumulate operation. This is nowadays performed with GPUs. They work very well. However, they suffer from what is called the von Neumann bottleneck. Basically, data is saved into the memory. And if we want to perform calculation, we need to move this data from the memory to the processor, perform calculation, and then save the results back into the memory. Going back and forth like that takes time and energy. And our goal is basically to remove this distance and perform calculation directly into the memory. For doing that, we are actually using a huge variety of technologies. These technologies, which are, for example, called memory stores, memory resistors, so devices where we can actually store in a non-volatile way information, are, for example, RAMs, devices where we create or destroy a filament between two electrodes. Phase change memory, we change the crystalline or amorphous structure of the material. Magnetic devices, we change the spin polarization of one layer and we get high or low resistance levels. And then, for example, ferroelectric memories, where we actually change the polarization of a ferroelectric layer. Actually, there are many more devices, but the slide was too long. What is interesting to know is that these devices were not developed for neuromorphic computation. These devices were developed for memory. And I think at least in the last 15, 20 years, there have been a huge amount of study on these things. For memory, we typically have these devices organized in crossbar arrays, where devices are in series with a selector. And if we want to read a particular device, we use an address decoder. This address decoder applies a small voltage. This generates a current, and the current is collected through these sense amplifiers, which are circuitry developed to distinguish discrete levels, because memory is a binary memory. Even a multi-level memory would be still a discrete memory. For neuromorphic computation, what we want to do is basically use the same crossbar array scheme, but we want to change some things. First of all, we need to change the peripheral circuitry. We will change these circles here. The weight is encoded as a difference of two conductances. Why do we need to use two conductances? Many explanations, but one very easy is basically the weight can be positive and negative, while conductance of a device can only be positive. So we use the difference of two conductances. If we want to perform this operation, sum of x times w, since the weight is encoded in the conductance, if we apply a voltage V, the product between V times G generates a current. So this product is actually performed by Ohm's law. To perform the summation, we basically turn on every word line, and so all the currents are then summed through Kirchhoff's law, and we actually get the total amount of current in the output neuron. What is important is that the output neuron needs to perform an analog measurement. It's not a discrete measurement. Now, this structure is very interesting. This is the core idea of why we use crossbar arrays, because here we can actually map one fully connected layer very easily, and we can perform all this operation in one single operation, in one single time operation, irrespective of the size of the layers. We just need to build a larger crossbar array if we want to do larger networks. However, we do not want to train one single weight layer. We actually want to train deep neural networks. And deep neural networks have many weight layers. For this reason, we need to have a chip which basically encodes many different non-volatile memory cores, each of them representing weight layers. Even if we have this kind of structure, we still need to satisfy some specifics to get something competitive with the existing GPUs. And in particular, we want something that is low power, so a chip that does not burn a lot of energy. It must be faster not only of actual technology, but also of next node's technology. And also, it must be also as accurate as GPUs in training neural networks. There's no point in doing something that goes super fast, but then it trains very sloppy. So if we have something that is only fast, only accurate, or only low power, this is very bad. It's not interesting. If we have something which is, for example, accurate and low power, but is not faster than existing technology, this is still useful in many power-constrained situations, for example, cars, drones, embedded systems, any case where we need a limitation in the power consumption. If we have something which is accurate and faster, but not low power, this is interesting also, for example, for servers and situations where we want performance, not power saving. If we meet all the three requirements, we are very happy, and we have something that makes exactly the job of GPUs. So let's start from the accuracy. Basically, we would like to train as accurate as GPUs, and this is important. So going back to 2014, this was the first result from the group. Basically, they were implementing a simple 4-layer fully connected network with this kind of weight structure, so two PCMs, G plus and G minus, encoding the single weight. This is the accuracy obtained on 5,000 examples of the NIST data set, so that's a very easy problem. And the accuracy we get is 82%. 82 is interesting, but it's very bad if we compare that with what we get with the corresponding GPUs. So GPU on 5,000 images would get around 94. So we are very far away from the target. The reason is that devices are really non-ideal. So they work in a way that we really would not have. Let's try to understand a little bit more why they do not work. Here, we basically see many conductance traces as a function of the applied pulses on the device. So we can notice that these conductance traces from many devices are, first of all, very noisy, and second, they are really nonlinear. The black line is just the median of the curves. So we basically have G plus having this behavior, and G minus also having this nonlinear behavior. Now, what does this mean from a neural network point of view? Let's suppose we have a weight like that, where G plus is represented by this green dot and G minus by this red dot. If we ask, please increase the weight, we will apply a pulse on G plus, but here the change will be small because the device is almost saturated. Then if the network asks, please compensate that previous pulse with another pulse, so what we need to do is basically, let's apply one pulse on G minus. But this would lead to a large change because here the device is very sensitive. So basically we have an asymmetric update, and this for training is very bad because basically we freeze the network. We cannot train after a certain amount of images. So here, this is not very good. Let's try to understand a little bit better and how can we develop a metric for defining those things. In this figure, we basically have one weight described with two PCMs, and we apply a certain amount of pulses, which corresponds to a plus 10 net pulses. So we ask the weight, please increase a little bit. This increases, great, and we can define the sum of weight updates, which is basically the difference of the last value minus the initial value, and it's positive. If we just perform this simulation many times, we get a distribution, and we can plot a very noisy distribution. We can plot this histogram of the weight updates, and you can notice that this distribution is broadened. The vertical value, so this delta, is the corresponding value in case we have an ideal device, so a perfectly linear and symmetric device. If we just repeat this same simulation, but instead of using a positive request, we ask, please decrease a little bit, this is the corresponding distribution of weight updates. You can notice that this distribution is also broadened, and very bad thing, is completely overlapped with the positive one. So in all this region, our weight structure is not really able to distinguish backpropagation requests. So if the network asks, please increase, sometimes the weights actually decrease, which is bad. In this case, basically, we have an accuracy on a 4-layer fully connected network, 98% for TensorFlow, less than 94% for the 2PCM scheme. So this is actually not working. What we decided to do is basically to extend the structure of our weight, including these two structures, 3T1C structures. So 3 transistors, 1 capacitor. Now we actually have the sum of 2 pair of devices. One corresponds to the PCM part, one corresponds to the CMOS part. This new structure is interesting for many reasons. The first one is that this kind of weight structure is much more symmetric for weight updates. We basically perform weight update only on G+, and loading or discharging a capacitor is a much more linear operation than just acting on the PCMs. Second interesting thing is the dynamic range. So basically now our weight can be much can have a larger dynamic range because we can go to larger and smaller conductance with negative sign thanks to this gain factor, which is just a way to increase this part of the weight. Finally, the non-volatility of this weight is still preserved because we all know that capacitors leaks in basically some milliseconds. But when we train at a high speed, around hundreds of nanoseconds per image. And what we do is, after thousands of images, we can just stop for a microsecond. We can read the entire weight, and we can store the entire value in the 2 PCMs. If we do this, what happens is that we save the entire value in the non-volatile part of the weight, and we preserve this part to saturate, because then we can actually restore them to 0, and we can continue training. Now, since we are doing this transfer operation only once every thousands of images, we can do that a little bit more carefully in what is called a write and verified way. So basically, we write, we read what we have written. If it is correct, we stop. If it's not correct, we just continue writing until we get the exact result. Now, let's focus a little bit more on training. So we just take a look at this structure. Basically, here we have a capacitor which is charged by this PMOS, discharged by this NMOS, and then we read the output conductance through this output transistor. Now, in a perfect world, we would be able to define this transistor as completely equal to this one, and this would provide the same current that this one provides. This would lead to basically balanced weight updates. If we just consider this model, we would have this kind of traces by repeating the same simulation as before. So if we ask, please increase, now the curves are much more tighter. And if we also ask, please decrease, also in this case, results are fine. And the corresponding distributions of weight updates are now distinguished, which means that we are actually able to understand if backpropagation is asking, please increase, we will increase the weight, and please decrease, we will actually decrease the weight. This would actually lead to a very high accuracy, which is even higher than what TensorFlow can get. So we were actually quite happy with this structure. However, after that, what happens is that in real life, the curves are not like that. We actually have a huge amount of variability over transistors. This corresponds to 90 nanometer technology variability, so this is something similar to reality. In this case, the worst problem is that the PMOS and the NMOS will never provide the same amount of current, and so will never be balanced for weight updates. Given this in mind, we basically repeat the same simulations. These are horrible. Good for making a nice picture, but they are horrible because we are not very good even in understanding if this is the family of increasing or this one. So they are basically the same thing. Now, variability destroys actually the result, and we are around 92%, which is even less than what PCM could do. So at this point, there was a huge amount of depression in the lab. And we decided to understand a little bit more why is this happening. Basically, we just pick...
Quick question, though.
Yeah, sure.
Is this measured data you're showing, or is this based on your Monte Carlo?
This is Monte Carlo simulations. And so what we do is basically we extract...
And even more depressing if you fabricate the picture.
Yes, yes. But I'm sure it will be depressing one day. So basically, if we just extract the outliers of this family, so the first, the last, and one intermediate, we just plot them here, and we try to understand why they work so bad. So let's take this one, the MFET curve. Basically, what happens here is that even if we are asking, please increase the weight, what happens is that the NMOS is so strong, so provides such a large amount of current that actually he discharges completely the capacitor. And similar in this other curve, here the PFET is much stronger. While here, the nice situation, the PFET and the MFET basically provide the same amount of current. So what we notice is that, for example, for this curve, we are actually having a super strong MFET. What we can do is play a trick, which we call the polarity inversion. Instead of using the MFET for decrease the weight and the PFET for increase the weight all over the time, what we can do is actually swap the roles of the PMOS and the NMOS once every, for example, 8,000 images. If we do that, basically what happens is that you can see here. Before, the MFET in the first phase was asking, reduce the weight a lot. But in the second phase, it will actually ask, please increase a lot, because it's the same MFET providing the same role. So at the end, the curves will actually be much tighter and nearer to the ideal case. If we do that, basically what happens is that these are the same simulation as before with the new technique. Now, the distributions are much less overlapped, the distributions of weight updates. And in this case, we are actually much better at distinguishing the requests from backpropagation. In this case, with this technique and using full variability, we still have an accuracy which is basically the same one as TensorFlow. So this structure is promising. What we did then is basically demonstrate that with a mixed hardware and software experiment. What does it mean that? We basically simulated with SPICE the circuitry, the CMOS circuitry, and then we used real PCMs, so real phase change memory devices. For example, for training MNIST, in this case we use 300,000 devices. And in this case, TensorFlow curves are basically very exactly equivalent to what we get from our lab. This is for MNIST, this is for MNIST plus noise. Here we are near TensorFlow results. We also performed transfer learning experiments, so we basically pick a huge convolutional network and we retrain the last layer on a different data set, initially on ImageNet, and we retrain on CFAR 10 and 100. Here we have equivalent results. Here we are quite near, around 1%, CFAR 100. Now, this demonstration is nice, but I'm sure all of you are asking, yes, this structure, however, is huge. It occupies a lot of area. Would be nice to use only 2 devices. So go back to the ideal scheme of 2 devices. So a colleague of us, Typhoon Gokmen from Yorktown, actually calculated what would be the ideal devices that we actually need for this kind of training operations. We would basically need 1,000 different conductance levels and an asymmetry of 5%. Now, this number is simply nonsense for device community, because if you think that there has been a huge amount of study and effort from companies and academia to develop a memory with this kind of technologies for 1 bit, so 2 levels, a maximum was actually 3 bits, so 8 levels. You understand that, and it was not so easy to do that, only Intel performed that. In this case, we are asking for 1,000 levels, so that's simply very, very far away from what we think. The approach we use actually diversifies the requires on devices. We actually have a most significant pair and a least significant pair, and we are asking different things for those devices. In particular, what we could do is, instead of going back to 2 devices, we can go back to 4 devices. 2 devices for MSP and 2 devices for least significant pair, LSP. Those devices would actually be characterized by infrequent and closed loop programming, while these other 2 devices would have actually frequent and open loop programming. So we're actually asking different things. More precisely, for the MSP, the most significant pair, we don't need a linear conductance update. We just need to have a device with a high retention and able to be programmed in a closed loop fashion. For the open loop schema instead, so for the LSP, we can use devices with poor retention. This is absolutely fine. We are updating device every hundreds of nanoseconds. And if we have fixed variabilities, like one device has a conductance which is much larger than the other one, there's no problem, because the polarity inversion actually averages out this kind of tricks. However, we need a device with a high linear conductance update. Just to provide an example, if before we were asking for 1,000 levels, with this new scheme, we actually ask for 100 levels. It's still a very difficult target, get reliable 100 levels, but it's 1 order of magnitude better. Now, just to conclude something about circuits, we basically want to be faster than actual technology. So we are discovering these devices, and they are actually great for performing calculation. But we also need to have a circuitry which goes fast, because if we are super fast in calculating here, and then we spend a huge amount of time to communicate results to the other core, we actually waste all our advantage. So our approach is basically we need everything parallelized, no multiplexing. We avoid analog to digital conversion to avoid time, power, and area consumption. And then we would like to simplify the neuron, because if we want to do parallel structures, we also need to do compact structures, and we cannot do very complex circuits for neurons. Finally, we noticed that digital accelerators work very well for convolutional layers. Thanks. And then what happens is that we are not very good for convolutional layers, because convolutional layers use a small amount of weights, and we are good in situations where we have a huge amount of weights. So the best thing we can actually think about is putting them together. Digital cores for convolutional layers, analog cores for fully connected layers. This, and this is just a thought, but we know that the networks we are using nowadays are the networks which we can train on the hardware we have today. We use a huge amount of convolutional networks because basically GPUs are very good at that. And we want to reduce the amount of fully connected layers because they are very expensive to train. If we provide a hardware that can perform easily the training of fully connected networks, it would be nice to, for example, have a different balance between a huge amount of convolutional layers and just 1 or 2 fully connected layers. And this is something that we can only hint. We don't really know what's the answer here. So just to conclude, we basically demonstrate that our approach with non-volatile memory devices can speed up the training, and we also demonstrated software equivalence on small and medium data sets. That's a group. Thanks so much.
Okay, thank you very much. That was a wonderful talk. Floor is open. Okay. actually, German is easier.
It's an unfair advantage of sitting in the first row, sorry. So quick question. Well, thank you, first of all, for very informative talk. You're kind of answering my question that I asked before. What kind of constraints people developing machine learning algorithms should know?
Huge amount of constraints.
Yeah. So we actually try to discuss with Typhoon a little bit. So one way to go could be try to actually develop algorithms that are not based on backpropagation, or basically different optimization algorithms that might be a little bit more maybe stable to those kind of uncertainties and biases. Well, actually, you try to remove the bias by switching the roles, and so you kind of randomize it. I think it's a very clever idea. But in general, did you also try to work with anyone on pretty much just developing different optimization algorithms to implement learning that might be better fit for the constraints that you have?
Well, absolutely, there's a kind of job like that in IBM, and actually Typhoon is one of, for example, people doing that. And we want to have some algorithm that actually works better, but it's not very easy to substitute an algorithm which works since 40 years and it's proven to work very well with something different just because we have a problem in devices. So it's hard because you need to demonstrate that the new thing works as good as the old one.
There is a whole field of optimization, and there are many ways to skin the cat besides backpropagation.
Well,
but it's a separate discussion. And okay, so maybe we could also discuss it offline. But it's extremely important, the hyperparameters like learning rate and other things. And there are like tons of flavors of SGD, Adam and Nesterov method, and so on. And that can bring a huge difference here. So maybe we can discuss offline, because I was curious about you making sure the hyperparameters and everything is exactly the same, because that.
Well,
and how it's implemented in terms of like learning rate and its effects. But
that's a very important point.
Okay, they're too detailed questions. I think we should take them offline.
In the end, we did run. Thank you. No more questions, because in the end we did run a little bit late. So let's thank the speaker again.